So students, we are going to start with lecture number 28 today. But before that, we are going to continue the missed topics from lecture number 27. So in lecture number 27, we have started with three-phase circuits. And in that, the first circuit was three-phase star-connected system. So this is my three-phase supply. I have shown you last time, which connected via three coils. R, Y, and B are the three phases. Then this network is three-phase star-connected balanced load. Now, what do you mean by a balanced load? Balanced load means this Z phase in all three are equal in magnitude. Okay, they are having same magnitude. Also, there are line voltages, phase voltages. So over here, my phase voltages are with respect to neutral, VRN, VBN, and VYN. So these are my three phase voltages. Line voltages are via sequence, RYB. So VRY, VYB, and VBR. These are the three line voltages. All right. And we have the three currents also, line and the phase current. So IR, IY, IB are all three line currents, that is equal to phase current. So in a series network, the the current remains the same. So line current and phase current are same, but line voltage and phase voltage are different. All right. Then we have said this that as the phase is different, as the load is balanced, we can write V phase is VRN is equal to VYN is equal to VBN. I think we have revised this topics before and we have written this equation. So only the magnitudes are same, but how do they differ from each other? They differ from each other by 120 degree. So VRN is V phase 0 degree, VYN is V phase angle minus 120 degree, and VBN is V phase minus 240 degree. Got it? Three line voltages are VRY, VYB, and VBR, and all are same. So what we are doing is we will write VRY as VRN minus VIN. Okay, please concentrate on this. VYN can be written as minus of VNY. So this minus minus become plus. So VRY dash is VRN minus VYN or VRN plus VNY. So that's what we have written over there. What are we doing over here is establishing a relation between line voltage and phase voltage. So VRY dash is VRN minus VYN. VRN is V phase angle 0. VYN is V phase angle 120 degree. This is in polar form. We cannot subtract in polar form, convert into rectangular form. So what do we get is V phase plus J0. And here if you convert it into rectangular form, you will get minus 0.5 V phase minus J 0.866 V phase. And if you club them together, you will get VRY is 1.5 V phase plus 0.866 V phase. So if you convert this rectangular into polar, you will get root 3 times V phase 30 degree. And all the line voltages, that is, write this down equation, VRY is root 3 times V phase angle 30 degree. So all my line voltages are differing from the phase voltage by 30 degrees. Is that clear? You will have written these things? Okay, alright. So in summary, in a star connected system, the line voltages leads the respective phase voltage by 30 degrees. So VL is root 3 times V phase and the line current is equal to the phase current. Now write down phasor diagram of three-phase star connected system. Please write it down. Please write it down. Phasor diagram for three-phase star connected balanced system. And we have to be very careful in drawing the phasor diagram for this. Okay? Written the heading. Also, we are assuming one thing. We are assuming inductive load. I don't know whether you can see that or no. What is the advantage of an inductive? We are using inductive load, so that means that three-phase balance load, star-connected load, is like this. Yeah, I know it. I know it. So I'm not concentrating on that. I'm just explaining that it's a inductive load. Inductive will be RL load practically because inductor coil has a resistance. So this load is like this. That's what I'm explaining over here. This contrast is fine now, the black color. Yeah. So this is my load. Okay, this is the RL load. And this we call it as Z phase. So what will be Z phase? R plus JXL. Are you getting it? So that's what the meaning of inductive load means. This can you see what I've written over there? Okay. So here we have written VRY. Write it down. VRY is equal to VRN plus VNY. We have seen that before. Then V by B bar is equal to VYN plus VNB. Now can you see? Okay. VBR is equal to VBN plus VNR bar. You have written up till here. So it's an inductive load, and we have written the three line currents. Okay. All right. All of you ready? So first we'll draw. Listen carefully. Now, a complete attention. Please, everyone, concentrate please on the board, because I won't be able to repeat it again and again. So please concentrate only once. We are trying to draw the phasor diagram for a three-phase star-connected system. So the first thing which you draw over here is phase voltages. What are the phase voltages? VRN, R by B, right? VRN, VYN, and VBN, R by B. Okay, with respect to neutral, and they differ each other by, they have same magnitude but differ each other by 120 degree. So please draw them please over here. So let me take a little more space. Yeah, this much is fine. So I will draw VRN like this. Let's say, let me take it a little steeper. This is VRN bar. Where I will draw, I'll just little bit at the highest this thing. Yeah, where I will draw VYN or VBN 180 degree apart. Okay, so 180 degree apart will be somewhere around here. VBN and somewhere around here. This is the first thing which you do. Draw phase voltages, and they differ each other by 120 degrees. So this is 120 degree. I'm showing it once only. Okay, all of them differ by 120 degree, having same this thing, same magnitude. Okay, even if it seems different, it's same. Got it? Understood this? Okay. Next, what will you draw? Next. Okay. So what you do is, you have drawn these things, right? Next, extend the mirror image. So what is the mirror image of VRN, VNR? So draw it with dotted line like this. Are you understanding? This is V and R. Okay, draw this dotted line. VBN mirror image will be VNB bar. So draw with a dotted line over here. Please follow the instructions and draw it along with me. V and B. And over here, similarly, you will draw VYN. Mirror image will be VNY. Please listen carefully and follow the instructions, please. So this is VNY. Correct? Yes? Please draw it up till here. You're learning this concept for the first time, so please concentrate. Blue color you can see properly. Dark blue, okay. Understood? Three phase voltages and the mirror images you have to draw. Now, next, what is VRN? Can you see over here? What is VRY? VRN plus VNY. Matlab, it will be in the middle of them. law of parallelograms if you see. So VRN is over here, VNY is over here, so VRY will be over here. Got it? Correct? And how will you join them? Like this. Are you following? And what is the angle between them? What is the angle? 30 degree. Because this is my line voltage. Line voltage differ from phase voltage by 30 degree. Understood this? Now similarly, VYB is between VYN and VNB. So VYN is over here, VNB is over here. So it will come in the middle like this. Okay? So I mean little bit longer. You draw by scale, it will come properly. So what is this? VYB. Got it? And last listen. VBR is VBN plus VNR. Where is VBN? VBN. And what is VNR here? So last will come over here. So this will be VBR. And how will you join them? Like this. Okay? So my phasor diagram looks like this. If you follow the proper scale and take 120 degree properly, you will get a proper graph. But one thing is left, current. For an inductive load, current is leading or lagging the voltage? Tell me. Lagging, behind. Okay? This much you have understood how to draw? Everyone? So these three equations are very important. Now please listen. Please listen. So we are drawing, we have assumed the inductive load. So where will I draw the current? Current I will draw with respect to phase voltages. So current will be over here. IR. And this phase, this will be the phase angle. Where will be over here? Here. This is I B. This is phase angle phi. And last will be over here. I by phase angle phi. So this completes my phasor diagram. Okay. Assuming inductive load, my current will be lagging behind the voltage by less than by phi, but less than 90 degree. Assuming an inductive load. So please complete this phasor diagram. If they ask this question, they'll definitely have to draw the phasor diagram for three-phase star balance connected load. Okay? Understood how to draw it? It's very simple actually, not so hard. If you by heart it, then it's become hard. First we started with VRN, VYN and VBN, 120 degree apart. But then we drew the mirror images of VBN, VRN and VYN. Then we drew the line voltages, the resultant line voltages, and finally we have drawn the current, which is lagging behind the phase voltage by an angle phi, phase angle phi. Completed? Yeah? So I hope it is clear. Now write down power. Power in a three-phase star-connected balance system. So the important note is, in a three-phase star-connected balance load, power consumed in each load phase is the same. Okay, so all the three phases are identical. Since all the three phases are identical, the total power is the sum of the power in the three phases. So what is the power in each phase given by? What is the power in AC circuit given by? VI cos phi. Okay, and here what is the power? V phase, I phase, cos phi. Write it down. So since three phases are equal, power in the entire three-phase star connected will be 3 times the power in each phase. So 3 times V phase, I phase, cos phi. So write down this power formula. You have understood why 3? because all the three phases are identical and power in each phase is Vi cos pi. So there are three phases, so 3 times. So the active power will be 3 V phase I phase cos pi. Please write it down quickly. Okay? This is the power in terms of phase voltage and phase current. But for a star connected network, VL is root 3 times V phase, IL is I phase. So wherever there is V phase, I'll substitute VL by root 3 and I phase ki jagah IL. So if you see carefully, power in a 3-phase star connected system in terms of line voltage and line current will be root 3 times VL IL cos pi. Please write down this formula also. Okay? Active power is root 3 VL IL cos pi. Sir, can you tell me what is phi over here? Phi is the phase difference between what? Is the phase difference between phase voltage and the corresponding phase current. Okay? Completed? So draw the power triangle. Reactive power will be, see, we have done this before. Reactive power will be Vi sin pi. Okay? So here it will be 3 times V phase I phase sin pi, or in terms of line current and line voltage, root 3 times VL IL sin pi. And what will be apparent power? V into I. In a 3-phase network, it will be root 3 VL IL or 3 times V phase I phase. Write down everything. All the formulas write down. And finally, draw the power triangle. You know na S, Q and P? S is the apparent power, Q is the reactive power, P is the active power. And the unit. So please write them down. Note it down. Completed? Please note it down. So this is a power in a 3-phase star connected balance system. All right. So this was the pending topic from lecture number 27. Now let's start with EEEE lecture number 28. Yeah. And now we will start talk about 3-phase delta connection. So please write down. 3-phase delta connection. So how do the 3-phase delta supply look like? Anyone? Like a delta supply, right? So it will look like this. It will consist of 3 coils. Remember, we are drawing delta connected. So this is my R, this is my Y, and this will be my B. R, Y, B. Please draw 3-phase delta supply. R, Y, and B. You remember in a 3-phase supply, we use 3 coils. So this is B1, B2, R1, R2, Y1, Y2. You notice one different thing in case of a 3-phase delta connection, there is no neutral. Correct? There is only R, Y, B only. So it's a 3-wire system. Whereas in case of star, you have R, Y, B and neutral, right? Here there is no neutral. Okay? So over here, the 3-phase voltages are equal in magnitude but differ from each other by 120 degree, right? Have you drawn the supply? So write down, this is three-phase delta connected supply. Write down the below heading. It's three-phase delta connected supply. From now on, if I write R by B, three-phase supply, it can be delta or star. If it is a delta connected load, I'll connect a delta connected supply. Are you understanding? And if it is a star connected load, I'll connect a star connected supply. Write down over here, VR is Vm sin omega t minus 0 degree. Vy is Vm sin omega t minus 120 degree. And Vb is Vm sin omega t minus 240 degree. You have written it before, please write it down. And if I combine all three together, it will be 0. VR plus Vy plus Vb is equal to 0. We have done this before, so if you want to just write the result, VR plus Vb is equal to VR plus Vy plus Vb is equal to 0, you can note it down. Okay? So can we go to the voltage, current and power relationship in a balanced three-phase delta connected system? Please draw this diagram. What are we trying to determine now? Line voltage and phase voltage relationship, line current and phase current relationship in a three-phase delta connected system. Okay, so this is three-phase delta connected supply. Three-phase delta supply. So I'm not drawn again. I've just written that three-phase delta supply. And this is my three-phase delta connected load. Now please concentrate and write it down. Yeah, students, please concentrate. Those who have come late, please don't disturb the class. Again, what is the meaning of balanced load? Balanced load means the Z phase is all same. Okay? So it's a three-phase delta connected balanced load. Okay. So over here, can you see that red color, whatever I've written over there? That's orange color actually. So in this case, my phase currents and line currents are different. So what are my phase currents? VRY, write down. VBR and VYB are phase currents. And my line currents are IR, IB, IY and IB. So please write down line current and phase current. So this is three-phase delta connected balanced load. Write down the line voltages VRY, VYB and VBR. So since the load is balanced, all my line voltages are same. So VL is equal to VRY is equal to VYB is equal to VBR. Please write them now. And here, since this is a delta connected system, my line voltage and phase voltages are same. My line current and phase current are different. So write down in a three-phase delta connected system, line voltage is same as phase voltage. That means VL is equal to V phase. Alright. Next, write down as the load is balanced in a parallel, in a delta network, my current is different, but my voltage is same. So as the load is balanced, all the three phase currents are equal in magnitude but differ from each other by 120 degrees. So write down IRY is equal to IYB is equal to IBR is equal to I phase. And how they differ each other? By 120 degree. So IRY dash is I phase 0 degree. IYB dash is I phase minus 120 degree. IBR dash is, IBR bar is I phase minus 240 degrees. Please note it down. In a star connected system, we were establishing a relation between line voltage and phase voltage. Here we are establishing a relation between line current and phase current. Now write down three line currents are IR, IB, IY and IB. And they are same in magnitude. Okay. Now, if I want to mark over here the various currents, how will I show it? Let me mark it in, these are my voltages, VR by line voltages, VYB, and then it is VBR. Okay. My three line currents are IR, IY, and IB. My three phase currents are IRY between phase R and Y, then IYB and IBR. So these are my various phase voltages, line currents and phase currents. Please mark them in the diagram. Have you marked them? Okay. So if I apply KCL at node R, if I apply KCL at node R, what I will get? This is my node R. Okay. So if I apply KCL over here, what I will get? There are two incoming currents, IR plus IBR, and I have one outgoing current, IRY. Alright. So what is IRY given by? IR plus IBR. Are you understanding? KCL at phase Y is IR plus IBR. IRY is IR plus IBR. So I've written over here IR plus IBR is IRY. So IR is equal to IRY minus VBR. Okay, and IRY is I phase 0 degrees, angle 0 degree, and IBR bar is I phase minus 240 degree. Now you convert this into rectangular form, so you'll get I phase plus J0, I phase angle minus 240. If you convert into rectangular form, you will get minus 0.5 I phase plus J 0.866 I phase. Now club them together, you will get IR bar is 1.5 I phase minus J 0.866 I phase. And if you convert it back into polar form, you will get root 3 times I phase angle minus 30 degree. Okay. So please note it down. IR bar is root 3 times I phase minus 30 degree. Similarly, we can apply the KCL at the Y phase and B phase. You will get IY plus IRY is I by B. Okay, so IY will be I by B minus IRY. That will be again root 3 times I phase minus 30 degree. You can prove it. And IB plus IYB is equal to IBR. Again, you will apply KCL at B, at phase B. So IB will be IBR minus IYB. That will be again root 3 times I phase minus 30 degree. So in general, we can write in a three-phase delta connected system, line current IR, IB and IY are 30 degrees, lagging behind the respective phase currents by 30 degrees. Okay. So write down IL is root 3 times I phase. Now next we draw the phasor diagram for a three-phase delta connected system. So again write down assuming inductive load. So IR will be IRY minus IBR. IY will be IYB minus IRY. IB is IBR minus IYB. Okay. So over here, again, first we have to draw the phase voltages, three phase voltages. So the three phase voltages are V by N. So please draw V by N. V R Y, sorry. Phase voltages are V R Y. Now there's a line voltage actually. We first draw the line voltages over here. Phase voltage and line voltage is the same over here, right? Then you draw V Y B, and again 120 degree apart you draw VBR. So phase voltage and line voltage in a delta connected system is same. So if I call it phase or line, they are means the same. So all three magnitudes are same and they differ from each other by 120 degree. Okay. Now how will you proceed forward? Here, phase voltage and phase current are different. Okay, line voltage and phase voltage are same. So here we have to draw with respect to currents. So now tell me, since it's an inductive load, current will be leading behind, will be leading or lagging. Inductive load will be lagging. So over here, what will you draw? IRY, current IRY. Okay. Similarly, here what you will draw? IBR. It is lagging behind by phi, angle phi, and here you will draw IYB. So these are my line currents: IRY, IBR, and IYB. You know what you have to do now? The mirror images of IBR, IRI, IRY, and IYB. So please draw the mirror images over here. So this will be minus IBR. This will be minus IRY. And over here, this will be minus IYB. Okay. Now, IRY, it's a vector sum of IRY and minus VBR. So IRY and minus VBR. So IR, the phase current will come over here, resultant of these two. Let me use red color over here. So this will be IR. Are you getting it? Okay. Next is IY. So this IYB, vector sum of IYB and minus IRY. So it will be over here. So this is IY bar. Please draw it along with me. Okay. And IB is IBR minus IYB. So here it will be vector sum. This will be IB bar. I will draw a little steeper, but it will be a vector sum of this only. So this is IB bar. All right. And what is the angle? Your between line current and phase current? 30 degree. So this is my phasor diagram for three-phase delta connected system. Completed? Again, in terms of power, since all three phases are identical, the total power is the sum of power in each phase. So the power formula, whatever you have written in star connected system is same, exactly the same. So power is 3 times V phase I phase cos phi and root 3 VL IL cos phi. Similarly, your power triangle also will be same. Apparent power is root 3 VL IL and reactive power is root 3 VL IL sin phi. Alright. So with this, we complete the three phase delta connected balance load system.